Good evening, Ms. Kempf here. In this section, we're going to think a little bit about motion in two dimensions. So just as a reminder, so far we've really only seen horizontal and vertical motion. Horizontal motion, we saw a lot of like cars moving and people walking and people running, and we saw two very specific examples. When the horizontal motion of an object is at a constant velocity, then their rate of change of position is constant. And with accelerated motion, we saw the velocity changing, and so their position was able to change more and more and more every second. And we saw even more, maybe a more complex example of this, where we saw, for example, we had a ramp and a car moving up a ramp. So it started at a really fast speed, slowed down, slowed down, slowed down, stopped for a fraction of a second, and then sped up in the other direction. And so we saw in that kind of example times when the acceleration was in the same direction as the motion, which sped it up, and times when the acceleration was in the opposite direction of the motion, when it slowed down. But still, the acceleration and velocity were along a single line. With vertical motion, we didn't see a lot of constant velocity, though it does exist, for example, in an elevator. But we did see a very specific case of accelerated vertical motion, and that is what we called free fall. So free fall, for just as a reminder, is when we had a very specific acceleration, negative 9.8 meters per second squared. And we had a mathematical way to represent this. So these three kinematics equations, we said, were three different ways to represent the motion, where each one is kind of missing one variable that we maybe don't care about. The first one, we don't seem to know anything or care anything about the displacement or the position of the object. In the second equation, we don't tend to know much about time, or maybe time isn't given to us. And in the third equation, which I think is maybe the most useful one, it's where we don't really care much about the final velocity. So these three equations allowed us to represent the motion of any object, where each one was a different tool that was useful to us in a different way. So is that still going to be the same as we move into like a two-dimensional, or really a three-dimensional world? And should we even bother with two dimensions before moving to three if the world is three-dimensional itself? Well, but actually most motion is two-dimensional even in our three-dimensional world. So for example, this woman who's walking, and previously we might have considered this to be one-dimensional motion. She really only moves horizontally, but if we look very closely, she actually sort of moves vertically as well. She has to push herself up off the ground before kind of coming back to the ground, and has a little bit more of like a hopping motion that we would expect from, for example, a bunny. But if you look very closely at her feet, for example, her feet have to push off at an angle. There's no way to walk, and I really encourage you to try it actually. Walk without pushing off at an angle. Try to walk completely with your feet horizontal, or completely with your tiptoes vertically. It's literally impossible. It's like trying to walk on ice. And so walking is really a two-dimensional object, which is not three-dimensional. She's not in any way kind of pushing into or out of our paper. Orbiting is actually a two-dimensional process as well. We know that all planets orbit on some sort of elliptical path, some of which look a little more circular, like ours does. But actually it's still two-dimensional. I could draw a flat plane right through the path of orbit, and define everything as some sort of horizontal and vertical combination of horizontal and vertical motion. And just as a preview, we're going to be getting into, in the next section, projectiles, which also move kind of in a horizontal and vertical direction. But none of these objects seem to move like into or out of the page in the third dimension. So it's actually a lot more common to see two-dimensional motion in our real world than three-dimensional motion, though it does exist. So as a way to think a little bit about these two dimensions, I'm curious about whether the motion in one dimension affects the motion in the other dimension, or can I completely think of them as separate? So one way to think about that might be imagining a boat crossing a river. So for example, if the river has no current and the boat points itself directly at the opposite shore, it just moves completely, what I would call in this picture, horizontally across the river. But what if the river does have current? So imagine the current is flowing in the vertical direction here, just to keep things positive. So now if I look at the motion of the river in the vertical direction and the motion of the boat in the horizontal direction, I can see that both sort of affect the motion of the boat, such that the boat actually moves in maybe this diagonal direction. So here's an example of 2D motion where the motion of the boat is horizontal, but the motion of the boat is also vertical due to the fact that the river is pushing it. So here we have an example of a two-dimensional case. And so I could define, for example, my xy plane like this in our standard way, x to the right being positive and y up being positive. But in this class, I hope that you've realized that it's helpful to be really skeptical. So you might be thinking, well, isn't this sort of still motion along a line? Like, what if I just rotate my axes such that all of my motion is in this diagonal direction? Like, the boat doesn't actually move horizontally or vertically, the boat actually moves in this diagonal direction. And then you could imagine this y plane doesn't even matter, and this is really just one-dimensional motion again. So, back to our original question, does motion in one dimension relate to the motion in the other dimension? Do I need to think about this as x and y, or can I just very simply define it as motion along a diagonal? So to think about this a little deeper, let's draw it out. Let's imagine some numbers. Let's put some real-life pictures into the scenario, and let's see what happens.
Okay, so here's our riverboat problem. So we've got the boat, he starts over here. We know that the river is flowing vertically in this direction. And so we know that even though the boat only drives horizontally, the river pushes him vertically, and so he has both horizontal and vertical motion. So let's just play around with some numbers here. Let's say that the velocity of the boat, we know this is horizontal, is 5 meters per second. Just picking some random numbers here. And let's say that the whole river is 100 meters wide. So very quickly we can see if he goes 5 meters per second and he needs to go 100 meters, then the total time of his trip is 20 seconds. Well, actually, maybe that's not so obvious. If he goes completely horizontally, then it makes sense that it would go 20 seconds. But what if he actually doesn't go horizontally? If he goes in this diagonal direction, we know he has to go a lot further. So maybe it's not so obvious that his time is the same. If he has to go further, maybe it takes longer. But don't forget that he's actually not traveling 5 meters per second in this longer direction. He's actually traveling faster in this diagonal direction. Well, how fast is he going? He's going the speed that he would be moving horizontally due to his own motor, but also the speed that he's moving due to the water's velocity. And so we need to kind of define some speed of the water. So let's say the speed of the water is, I don't know, 2 meters per second. So if he's moving 5 meters per second and the water pushes him 2 meters per second, how fast is he actually going? Well, let's do some quick, I can kind of draw this. So this picture right here is kind of showing the displacement of the boat. It's a, right triangle where I've got one leg of the triangle being 100 meters. I can imagine this is a right triangle, and this, well, I don't know how far he goes in this direction. But I can actually draw a similar triangle with a similar angle that represents not his displacement, but his velocity. So imagine I have a triangle that's not about how far he goes, but instead how fast he goes. Well, I know he goes about 5 meters per second in the horizontal direction, and I know that the water pushes him, well, actually I could probably make this to scale, about 5 meters per second, 5 blocks. I know that the water pushes him about 3 meters per second. Nope, 2 meters per second in the vertical direction. So how fast does he actually go is actually just another right triangle problem. So he must go this fast. That's how we add vectors from the very beginning of the year. So I can do a quick Pythagorean theorem here, and I can do 5 squared plus 2 squared equals this actual velocity squared. And so 25 plus 4 is 29. So the speed he goes must be the square root of 29. And I can find my calculator here real quick. And so the square root of 29 is 5.39 meters per second. You can check it on your own calculator. So with both velocities, he's actually going in this same theta direction as the direction of his motion, right? That makes sense, that his displacement and his velocity would be in the same direction. And he doesn't move 5 or 2 meters per second or 7, he actually moves 5.39 meters per second. So if he actually goes this velocity and he's going this further displacement, maybe he actually, if he's going much faster than he was before, maybe he actually makes it in less than 20 seconds. So let's see. How can we figure this out? Well, actually, since these triangles have the same angle, and since they're both right triangles, we know these are similar triangles. So by a little bit of geometry that you may or may not remember from freshman year, if these are similar triangles, there must be some scale factor that relates them. So if this side is 100 and this side is 5, the scale factor between them is 20, which means that the distance he must go in this vertical direction is also 20 times bigger than 2, which is simply 40 meters. And if he is actually going in this diagonal direction, I can do another quick Pythagorean theorem to see how far he actually goes. So, and my displacement is 107.7 meters. Okay, so how much time does it actually take him? Well, if he's going this velocity, we know the velocity is the distance divided by the time. Quick solve for time. Time is velocity. Oh. Velocity times time equals distance divided by velocity. So I get time equals distance divided by velocity. Well, we know he goes 107.7 meters divided by his speed, which is 5.39 meters per second. Notice the units end up with seconds, so that's a good sign. And if I do some quick math, exactly 20 seconds. Especially if I didn't round any of my decimal places, which I did on paper, but not in my calculator. So it takes exactly 20 seconds. So even though he has to go farther, he's going faster and by the same proportion. Something else that's really clever for you geometry lovers, notice that the scale factor for our displacement and our velocity triangles was 20. Why was it 20? Because that was the time that we were traveling. If he needs to go 100 meters in the horizontal direction, and he's moving 5 meters per second, it takes 20 seconds. But think about it this way. If he's moving 2 meters per second in the vertical direction for 20 seconds, of course he goes 40 meters. And the decimal numbers work out exactly the same too with a scale factor of 20. That's what we just solved down here. So what's beautiful about this is that we can solve any of these problems using any of the dimensions we want. Some of them are sometimes useful, and some of them are sometimes not useful. So for example, you might have quickly found the actual velocity he travels, and if what you cared about was how far does he go, you could have solved it by using the actual velocity, the time of 20 seconds, and just simply finding the distance. So you could have used this as a one-dimensional problem where this is my x coordinate. But there's actually some really interesting things that happen if you think about the x and the y dimensions separately. For example, the time that it takes for him to cross the river is sort of embedded in this x dimension here. So for example, we know that no matter how fast the river's running, he's going to make it across the river once he travels the entire width of the river. If the river were traveling faster, maybe 3 or 4 meters per second, we know he's going to end up much further downstream, but it will still take him the exact same 20 seconds to cross the river because that's determined by how fast he's moving only in the horizontal direction. So sometimes it's clever, or sometimes problems necessitate the use of using the horizontal or the vertical or both And sometimes it's actually quicker to skip and use only the diagonal direction. So just remember that these are essentially tools that we have now. We can use kinematics equations like this velocity equals distance over time, or actually any of our kinematics equations in a horizontal or a vertical direction separately, or we can use it in any diagonal direction separately, and each one of those gives us a different problem-solving strategy.
Okay, so if I've convinced you, I hope I've convinced you that we can use these same mathematical kinematics equations in either dimension. So it would be really helpful for us to, when we're solving these on paper, know which dimension we're talking about, because if we're going to use the same equation in the x and the same equation in the y, our paper is going to get very complicated. So how about we just change these variables up a little bit? So here I've added a small subscript x to each of the variables that we're talking about so that I can write the exact same equation, but only be talking about, for example, here, the velocity initial in the x dimension, or the velocity final in the x dimension, or the acceleration in the x dimension. One thing to note is that I did not add a subscript to the time because, of course, it's dimensionless. And the displacement variable, delta x, that didn't change at all. Somebody somewhere chose x to be the displacement, and it would be very weird to have like x sub x. It already means displacement in the x. So I'm going to basically do the exact same thing for the y dimension, where I choose all y subscripts for my velocities, my accelerations, etc. But it would be, again, a little confusing for the displacement to be delta x subscript y, and so instead we're just going to use delta y. So here's a summary table down here of exactly how we're going to note each variable of motion in the x dimension and the y dimension, and notice, of course, that time is the same in both dimensions. This is also a really important layout because we're going to be using these types of tables to organize all of our information, because as you can see, we're going to end up with a lot of numbers here.